So we have new class members today, so make sure that you give them a big welcome. Today we're going to be covering a lot of different stuff, so I'm going to put this in one video so that you don't get overwhelmed by the sheer number of videos. But if this one winds up a little bit long, like a little over an hour, then what I recommend that you do is break it up into pieces. So the first thing that we're going to talk about is what a function is. Then we're going to discuss slope for a line. And finally, we're going to talk about the different equations of linear functions. So just be aware that this is broken up into different steps. So let's start with this idea of linear functions. So we've talked about linear equations, but now you're seeing this new word, function, here. So what is a function? Okay, well, first of all, the difference is that when we talk about linear equations, we only have this x, and now what we're doing is we're adding a y. So a function requires an input and an output, and our input is typically what we call our x values, and our output is typically what we call our y values. And this is just a set of paired data. So let's think about what some examples would be. We have Metro cards. So we have the cost of a Metro card, and we have, let's say, the number of Metro cards. So how much you're putting into the machine, or let me rephrase that. You go to a Metro card machine, it's the amount that you're putting into the machine, and then the output would be the number of rides that you get. Okay, an input might be your class, like Math 206.5, and the output might be, under normal circumstances, a room number. An input might be the textbook that you're trying to buy, and then the output might be the price of that textbook. So everything that we have has an input and an output. So input is our x and output is our y. That's typical. It doesn't have to be that way. So I could say my input is my R and my output is M. That's fine. We can do that. We can use different variables, okay? But most typically, and this is what you're probably most familiar with, we use X and Y. So let's just write that down so that you recognize what we're talking about, okay? So X is typically the input, and Y is typically our output. And when we talk about functions, what we're doing is we're saying for every input, there's only one output. You cannot have more than one. Okay. Some examples of functions in the real world, in the world around you. I don't like saying real world, but in the world around you, a perfect example is that Metro card. Okay, so you put in a certain amount of money. What comes out is a certain number of rides. Now, you may put in a different amount of money and get the same number of rides. So, for example, if you put $2.75 into the machine, you're going to get one ride. If you put in $3, you're also going to get one ride. That's okay. It's okay if different inputs give you the same output, but it's not okay the other way around. If you put in $2.75, you're only going to get one ride. You won't get one ride or two rides. You'll only get one ride. So this is one example. Amount of money you put into the Metro card machine. And then what comes out would be the number of rides. Okay. Another example would be textbook and price. A textbook is only going to cost one amount. And I'm going to add in the word new, because if we're talking about used, sometimes you could get it for all different prices, right? A class, let's say on Monday at 2 p.m. and the room number. So you can't have a class in two different places, right? Every class has to only meet in a single place. So these would all be examples of functions. Whatever you put in, okay, whatever you put in, there is only one possibility for what comes out. A textbook can't cost two different prices. A class can't be in two different rooms. You can't put in an amount of money and get two different number of rides, okay? So we have input creates an output. Okay. Okay, there are other ways that we write functions, okay? This is kind of like what you see in the world around you, but then we also have these mathematical ways. So a relation is any input to output. So if we have an input to an output, this we call a relation. A relation is a function when every input only has one output, okay? So these are functions. If instead we did something different, we put a subway train, okay? And we put the number of people. Okay, this is a relation that is not a function. And I say that because a subway train may have a different number of people depending on the time of day. So it might be that if you look at that subway train at 9 a.m., there are 150 people on it. But if you look at that subway train at 2 p.m., there are only 20 people on it. So you have an input, but now you have two different outputs, okay? Now we have lots of different ways that we show relations. We have 3 different ways that we could show a relation. One way is using sets, okay, which you have sort of been introduced to when we write the answer to an absolute value equation. We're writing a set. We can use just a relation, which you'll see with like bubbles, or you can use a graph. So I'm going to quickly show you examples of functions and non-functions using all 3, okay? So let's just take a bunch of examples and talk about whether or not they're functions, okay? So let's start with this bubble method. So what is this bubble method? Essentially, you have your inputs over here, and then you have your outputs over here. And let's say that your inputs are 1, 2, 3. and your outputs are 6, 8, 11. Okay. The way that we show the relation is we just draw lines. We say, okay, well, if our input is 1, then our output is 8. If our input is 2, our output is 6. And if our input is 3, our output is 11. What we're checking for, this is a 3, by the way. Okay. What we're checking for is that each input only gives us one output. So if we put in 1, we only get an 8 back. We don't get anything else back. Let's check that that's true for all of the others. For 2, we only get a 6 back. For 3, we only get an 11 back. So this is a function. Let's do another one. So I'm just going to abbreviate and just write I instead of inputs, but you should know what that means now. And O for outputs. Let's say that here we had 2, 6, 10, and here we had a 2 again, which is fine, 7, and 15. So here, if we input 2, we get 7. If we input 6, we get 7. And if we input 10, we get 2. Okay, let's see if this is if this is a function. So again, everything that we write here are now relations. It's whether or not we have functions. So here, a 2, an input of 2 gives us a 7. That's only one output. We're okay so far. And an input of 6 also gives us a 7. But it's only one output. We input 6, we only get 7. It's okay that we got 7 for 2 as well. It's that every input only gives us one output, and so far that's true. A 2 gives us only a 7. A 6 gives us only a 7. A 10 gives us only a 2. So this is a function, okay? Essentially what you're looking for is that only one line comes out of each input, and that's the case here. Let's take one more example. So we have our inputs and our outputs. This is 3, 7, 9. Let's make this 10, 11, and 5. Okay. And let's have 3 go to 10 and 5. 7 goes to 11. And 9 goes to 11. Okay, so let's look at this one. If our input is a 9, we only get an 11, so we're okay. If our input is a 7, we only get an 11, so that's okay. Remember, it doesn't matter if you get the same output. A 3, however, we've run into trouble because a 3 is giving us both a 5 and a 10. So it's the 3 that's causing the problem, okay? So you're always looking only at the inputs. And if you notice, there are 2 lines coming in of the 3. So this one is not a function. And why isn't it a function? Only because the 3 has 2 outputs. You have 2 lines coming out of that 3. Has 2 outputs. Forgot the word 2. Okay, so this is one way of writing a function. So we have our inputs, we have our outputs, and then we draw lines to show our relation. And we look, is there only one line coming out of each input? If there is, that relation is a function. If it's not, it's still a relation, but it's not a function. Okay? The other way that we could show functions is using sets. So an example, essentially what we're doing is we're using sets where we pair the input and the output together. So a set is always indicated with a brace. Okay, you're accustomed to that. So we have a brace, and then we have pairs of numbers, where the first number in the pair is X, and the second number in the pair is Y. And I'm going to put that actually on the previous page as well, where we have this input-output. The way that we write this as a coordinate is X, comma, Y. So that's what we're doing on the next page. We're writing this as coordinates, okay? So let's say that we have our first coordinate is 1, 6. Our next coordinates, so we differentiate between the coordinates with the commas, is 5, -1. Our next one is 2, 3. And our last one is 5, 4. So remember, our first numbers are our inputs, our second numbers are our outputs. So we're going to look at the 1. Now we know that the output for 1 here is 6. Now we have to make sure that 1 doesn't have any other output. So we're going to look at and make sure that we don't see any other 1s. And we don't. So 1 only has an output of 6. 1 is okay. Now we're going to look at the 5. Well, we see here that the 5 has an output of -1. We have to check and make sure that it doesn't have any other output. So we're going to go across here and we're going to say, wait, do we see 5 again? And we do. Here's a 5 and the output is 4. So if we look at these coordinates, we have one input of 5 and 2 different outputs of -1 and 4, which means this is not a function. So 5 has an output of -1 and 4. So here, when you look at the sets, what you're looking for is, are we repeating inputs? Because if there are inputs that repeat, then it's not a function. And as soon as you find one that repeats, you can stop looking. It doesn't matter if 2 only has 1 output or 2 outputs. It's already not a function. Let's take another example. Let's say that we had -3, 0, 1, 16, 5, 0, and 10, 2, and finally -1, 3. Okay, and again, we're going to look for inputs that repeat. So I look at the -3 and I don't see any other -3s, which means that 0 is the only output for -3. The same thing is true of 1, 5, 10, and -1. I don't see more than one of those as an input. Okay, now if you'll notice, you'll see 0 twice, but that doesn't matter because those are outputs. And it's okay to have the same output twice. You just can't have the same input twice. Okay, so this is a function. And we're saying it's a function because none of the inputs repeat. Okay. In the above one, we have a 5 that repeats. But down here, we don't. Nothing repeats. So this is a function. Okay. And then the last way that we show whether something that we could show a relation is using a graph, okay? So we could have graphs that are functions and graphs that are not functions, okay? Let's take an example. So our axes are our vertical axis. Sorry, I messed that up. Our x's are our horizontal axis. And our y's are our vertical axis. Okay. So when we do the pairs, we're essentially, it's like taking each of these coordinates and graphing them, okay? But we're not going to graph individual coordinates. We're going to actually create a set of coordinates. So let's take, for example, a graph that looks like this. Okay. So this graph is a function. How do we know it's a function? if I go to any x value on here, so if I go to an x value here, if I look at the corresponding y, meaning if I go up or down until I reach the graph, there's only one y value. I only hit the graph one time. These have arrows, but if you notice, you could kind of tell that even if I'm all the way out here on the axis, if I went down to try and reach the graph, because this graph, if we continue it, it's going to be somewhere down here, I'm actually going to only hit the graph one time, okay? So this would be an example of a function. Let's take another example. Well, now we're going to do the same thing. What we're looking for is at any, by the way, always label your axes. We'll talk about that at another time, but you should label your axes. This is something that your elementary school teachers were probably very strict about, and they should have been, okay? If we take any x value, so we go anywhere on this x-axis, and we go up or down until we reach the graph, what we're asking ourselves is, are we only passing through the graph once? And if we take an x value over here, then the answer is yes. If I go down, I only hit the graph once. But that's not true for every x value. If I come over here and I look at an x value over here, first of all, if I go up, I already hit it. And if I go down, I actually hit it 2 more times. So this x value has 3 outputs, okay? So we could say it's not a function because at this x value, we hit the graph 3 times. This input has 3 outputs. So it's not a function. Okay. What we call this is the vertical line test. It tests to see whether or not a graph is a function. So this is saying a graph is a function if we can draw a vertical line anywhere on the graph. Anywhere. And it only passes through the graph one time. Okay, if it passes through more than one time, it's not a function. Okay, so just as one last example, okay, here's an example. If we draw a line anywhere on this graph, will we ever have a line that passes through the graph more than once? Okay, and I'll give you a second to think. We do, okay? So an example of a line that passes through it more than once, and we only need one. If there's even a single line, then it's not a function. So this is not a function because this line passes through the graph twice. Okay. Okay, so something to realize. Every single line is a function except for a vertical line, because if it's a vertical line, it's going to fail the vertical line test on that line. Okay, so every single line is a function. Except a vertical line. Okay, and that would make sense because if we drew a vertical line at that vertical line, it would pass through, they pass through each other an infinite number of times. So every single line is a function except a vertical line. Now this is very important. This vertical line test is critical because we're going to be using this a lot to determine whether or not graphs are functions. Okay. Okay. This would be a good time to just pause, take a little bit of a break, and then you can come back again and start with us at slope. Okay. So the next thing that we're going to talk about is the slope of a line. So we said that the thing that differentiates a line from every other type of function, okay, or every other type of graph is the fact that it has a constant rate of change. So throughout this class, we talk about all different types of functions: linear functions, quadratic functions, logarithmic functions, exponential functions, trigonometric functions, rational functions. We just do lots and lots of different functions. The whole first part is these linear functions. So now we're going to start talking about the different aspects of a linear function. So the first thing, the biggest thing, is the slope, okay? Right? So a line has a constant rate of change. We call this constant rate of change a slope. Okay, and this is delineated, so delineated means represented. It's delineated by the letter M. Delineated or represented by the letter M. So instead of always writing slope equals, we can just write M equals. Okay, so let's talk about what this means. So first of all, I want to show you slope. Okay, so this is your line. This blue diagonal line is your line. And if we were to take 2 points and connect them using a horizontal and a vertical line, okay, then what we have here is we have the rise and we have the run. So the rise is always vertical and the run is horizontal. And the slope is your rise over your run, or your change in y over your change in x. So rise over run, it's a proportion, our slope. Okay. So change in y over change in x. Now I'm also going to write this as we say delta. This is a Greek letter that means change. So it's delta y over delta x, okay? And we can also call this rise over run. So let's just talk about what this means, okay? So let's say that our slope was 1 over 3. Okay, here's what this means. This means that as we go to the right by 3 units, we're going up 1. Okay, so for example, let's just show this on a graph very simply. I won't do this for all of them. So if we have a point at 1, let's say, so a point right here. As we go to the right by 3, I'm actually going to put this in red so that you can see it. As we go to the right by 3, right, this is going to put us at 4. We're going to go up 1. Actually, I'm going to take out that dot, because that's not really a new point. Sorry, this is so small. Okay. As we go to the right by 3, we go up 1 unit. Here is our new point. So this would be an example of a line with a slope of 1/3. Okay. As we go to the right by 3, we go up 1. If our slope were 2 over 5, this would be saying, okay, if we go to the right by 5, so if we add 5 to our x value, we're going to go up 2 on our y. A slope of 10 over 7. Well, this one says, okay, as we go right by 7, we actually go up 10. Now, when we talked about absolute value, we talked about direction, right? And we said the thing to change direction is a negative sign. So we always talk about it as going to the right because we always look at graphs going left to right. If we want to change the direction of the slope, we would say, okay, the slope is negative 2 over 9. It's still as we go to the right by 9. So we always read a graph left to right. But this time what we're saying is that we're going down by 2. And that down is because there's the negative sign. This negative tells us switch direction. We're going down now. So if we have m is equal to negative 11 over 3, this says as we go right by 3, we go down 11. Again, it's because of the negative sign, okay? And this is typically how we would write it. It would not be incorrect to say instead that when we go left 3, we go up 11, okay? So if you're going to the left here, then you're going up here when it's negative, okay? Then this has to stay consistent. It wouldn't be wrong to do that. We just typically don't do it that way, okay? So it would be okay. I'm going to write this in blue, that it would be okay to say as we go to the left by 3, we go up 11, okay? Because essentially what that's doing is it's saying, okay, instead of putting the negative on top, let's put it on bottom, okay? So a positive is to the right or up. A negative is to the left or down. If we put a negative in front of one of these numbers, then you're switching only one of the directions. So negative 11 over 3, it would be fine to say, okay, instead of switching the y direction, let's switch the x direction. So notice we're saying, okay, instead of going right, that means we go left by 3, but then we go up 11. We can't switch both directions. Now, if that whole thing was confusing to you, then don't bother with it. Just say, okay, as we go to the right by the bottom number, we're going up by the top number, or we're going down if it's a negative, okay? Okay, this was short, but again, this is a good time to take a break because now we're going to get into the actual equations of linear functions. So when we talk about equations of linear functions, we're not actually solving anything, okay? What we're doing is we're just writing out what a line would look like on a graph. So most of you are very familiar with y equals mx plus b. I know that if I meet somebody and they say, oh, what do you do for a living? I'll say I'm a math teacher. And the first thing that they'll say is either SOHCAHTOA, quadratic formula, which they never remember, or they say y equals mx plus b, because that's the thing that they remember when for linear functions, okay? And I've seen even in your homework from last week, I already saw one person where I said, y is, I think it was 3x minus 10. How do we know that that's linear? And they said, well, it's in the form y equals mx plus b, okay? So a lot of you are already familiar with this. So what is this? Okay, let's think about it. So first of all, we have 3 different ways of writing an equation. And the 3 different ways of writing the equation start with the information that you're given, okay? So let's start with the fact that you could be given a point and a slope. So let's think about slope, okay? So we already know that m is equal to change in y over change in x. So change in y, the way that we write this is the difference in the y values of our first point. And I'm going to reorganize this so that it's y2 minus y1. It doesn't really matter. It's just that in the formal way that we write the equation, it could be helpful. And then x2 minus x1. Okay, so if we have 2 points on a line, we can find the slope by subtracting the y values and subtracting the x values, okay? And we're using that here to help us, okay? The change in y is the difference between the x values. So if we go back here, the change in y would be this y value minus this y value. Whatever they are, we would subtract them. And that would give us this distance right here, okay? The change in x would be this x value minus this one. That would give you this distance here, okay? So we just subtract the y's and we subtract the x's. Which kind of makes sense because we're saying as we go to the right by this amount, okay, so we need to find this distance. We go up by this amount, so we need to find this distance, okay? Okay. So what we're going to do is I'm going to remove that middle piece and I'm just going to write m is equal to y2 minus y1 over x2 minus x1. If you remember this, then you'll be able to find every other equation for a linear function, okay? So here's what we do here to find the first equation. All we have to do is take both sides and multiply by x2 minus x1, okay? So we're going to take this side and we're going to multiply by x2 minus x1. And we're going to take this side and we're also going to multiply by x2 minus x1. And what that allows us to do is we can actually cross out the x2 minus x1 here. They're canceling each other out, and that's okay to do because there's this invisible parentheses around here. And remember, multiplication and division are they are at the same level. So we're taking the division, we're taking the x2 minus x1, and we're dividing before we're multiplying, but that's okay here, okay? So we could cross those out. And now what we have is x2 minus x1 is equal to, times m. I'll put the m over here. y2 minus y1. Now this pretty much gives us our equation. The only thing that we're going to change is that because we only have a single point when we're asked to write the equation of a line, and the equation of a line has to have x and y in it, we're just going to take out this y2. This x and this y just remain as x and y as our second point. Okay, so and we call this point slope form. It'll seem rather obvious because point slope form of a line, you need a point and a slope. So it's y minus y1 is equal to m times x minus x1. This is the point slope form of a line. Okay, so let's just take an example of how we might use this. Write the equation of a line with a slope of 7. Now remember, the denominator of 7 is 1. So we're saying as we go to the right by 1, we go up 7. That passes through the point 2, 3. Okay, so how do we write the equation? Well, this is a plug and chug. This y stays the same. It's still a y. Because remember, what we're doing is we're finding every single point on a line. Okay, not just one point, but every point. So we want a y and an x that just remain as variables. Okay, because then we're saying, okay, well, for this x value, our y is going to equal this. But for this x value, our y is going to equal this. It allows us to plug in all different x values. So y minus our y1. Now, we're only given 1 point. So our y1 comes from this point. The y value at that point is 3. We're told our slope is 7. And now we have x and then minus x1. And x1 is the x value for this point. Okay, so this 2, 3 is the same thing as x1, y1. Okay, that's our point. So it's a plug and chug. We take the y value from our point, we take their x value from our point, and then we have the slope. Let's say, for example, that this time we're told that, here's a first example. I'm going to save some writing, and let's say that our m is equal to negative 1/3, and our point is negative 4, 6. Okay, so same question. We're writing the equation of a line with the slope of negative 1/3 that passes through the point negative 4, 6. So we're doing the same thing. Here's our point. So it's y minus y1. So our y1 is 6 here. We go to our point and we look at the y value. So we have y minus 6 is equal to, then we have our slope, m, negative 1/3. And then we have x minus x1. So x, and then we have minus negative 4. So don't write it as minus negative 4. That's not really elegant. So the way that we write it instead is as x plus 4. Okay, let's do another one. This time, let's say that our slope is 3/8, and our point is 1, negative 8. Okay, so same thing here. Y minus negative 8. Well, minus a negative is a positive. So it turns into y plus 8 is equal to our slope, which is 3/8. And then in parentheses, x minus our x value, which is 1. Okay, and one last one, which I'd like you to pause the video and try on your own just to make sure that you understand it. Let's say that our slope was 4/5 and our point is negative 5, negative 9. Okay, try and write the equation of the line yourself first. So we have y, and then we have minus y1. So our y1 is negative 9. So minus negative 9 becomes plus 9. Then we have our slope, which is 4/5. And then x minus x1. So our x1 is negative 5. X minus negative 5 turns into an x plus 5. Okay? So this is the first type of equation for a line, the point-slope form. Okay, from here, we can do something called the slope-intercept form. And this is your y equals mx plus b. This is what you're familiar with. Okay, slope-intercept form. So let's talk about how you get slope-intercept form. Where does it come from? So it actually comes from point-slope form. And I want to point out that the point-slope form is the one that you should be most familiar with. Okay, this is the one that you use the most. It tells you the most. You don't need a lot of information. As soon as you get to the other two, you need a lot more information in order to write the equation of the line. So we actually prefer this, even though it's not the one you're most familiar with. This is the easiest one to work with, okay? Okay. So let's do slope-intercept form. So how do we get it? Well, a y-intercept is where our line crosses the y-axis. And the way that we write it is 0, comma, b. That's because on the y-axis, our x is 0, okay? So if we're trying to find the slope-intercept form, what we're doing is we're saying, well, actually, the point that we're given is 0, comma, b, okay? If we said that our y-intercept is 3, then we're saying that the point that we're given is 0, 3. If we are told that our y-intercept is negative 11, then the point that we're being given is 0, negative 11. So it's kind of the same thing. You're given a slope and a y-intercept instead of a slope and just any point. So let's take the point slope form. We have y minus y1 is equal to m times x minus x1. But sorry about that. If x1 comma y1 were 0 comma b, then this is what happens. Instead of y minus y1, we have y minus b. And instead of x minus x1, we have x minus 0. So just like in the previous ones, we plugged in the x value over here, right? The x value for the point, and then we took the y value and plugged it in here. We're doing exactly the same thing. It's just that our x value in this case is 0. So the 0 goes here, and our y value is b, so the b goes here. Okay, let's simplify this equation though. So in order to simplify, we can actually distribute the m. And we get y minus b is equal to m times x minus 0m, right? But 0m is just 0. Okay, well then our last thing that we can do is we can add b to both sides. And if we do that, then we get y equals mx plus b. And this is our slope-intercept form. Okay, where m is our slope, and 0 comma b is our y-intercept. Notice I always write the y-intercept as a coordinate. I don't just say b, okay? Our y-intercept is a point, 0 comma b, okay? Now, there are some things that should be that you could sort of see here. I can get slope-intercept form from the point slope form, right? By plugging in 0 comma b and then solving for y. I cannot go the other way. I can't get point slope form from slope-intercept form, okay? I can't say, okay, how do I get y minus y1 equals m times x minus x1 from here? okay? I wouldn't be able to do that. And this, you're given something very, very specific. For point slope form, you can be given any point, okay? And let's just do one example. I'm only going to do one because this isn't going to come up that much. Let's say that we write the equation for a line. Which equation you use depends on the information that you're given. So m equals 2. And y-intercept. Zero comma -3. Okay. So it's y equals mx. So our m is 2. And then our y-intercept, the b value, is just the y value. So we have plus b, so plus -3, which we can just write as -3. Okay. And again, which equation is going to depend on the information that you're given. If you're given a slope and any point, then you have to use point slope form. If you're given a slope and a y-intercept, then you're going to be using slope-intercept form. Okay. And the last one can't really be derived. Okay. So the last one is the standard form for a line. And what we say is this is a times x plus b times y is equal to c, okay? And a quick note is that this b is not the same as the y-intercept. And the second thing to note is a, b, and c must be integers. So if you wind up with fractions, you have to get rid of the fractions. Okay? And the x always comes first. So don't write it as by plus ax. Okay? It's ax plus by. Okay. So let's just take a look at this and go back and forth from one to the other. Okay? So I'm actually going to write these all together in one place. So we have point slope. Okay. Point slope form is y minus y1 equals m times x minus x1, where m is the slope. And our point is x1 comma y1. Okay, that's point slope form. And you will use point slope form when you are being told that you should write the equation of a line and you're given a slope and a point. Okay. Second thing that we have is slope-intercept form. So this is y equals mx plus b. This one you would use when you're given slope and you're given the y-intercept. And then finally, you have standard form. So this just puts it all in one place. These are the only forms that you would use. And standard form is ax plus by is equal to c. And this is just the requirement is a, b, and c are all integers. You may be given the equation of a line in standard form and be asked to convert it to slope-intercept form, for example. You would never be told, given this information, just go straight to standard form. You can't do that. You would have to put it in, let's say, point-slope form and then go to standard form, okay? So, in other words, we can do some conversions. If we get a line in point-slope form, we can put it in standard form. If we get a line in point-slope form, we can put it in slope-intercept form. We can also go backwards. If we have a line in slope-intercept form, we can put it in standard form. And if we have a line in standard form, we can put it in slope-intercept form. It is not possible to put a line that is in either slope-intercept form or standard form into point-slope form. Okay, so we can go from any form to another, except we can never take a line that we're given and put it into point-slope form. Okay, we can't do that. So we're going to just go back and forth between these different types of lines and look at how to convert from one to the other. Okay, and the way to do it is really to look closely at what the difference is between the equations. So we can go to slope-intercept and we can go to standard form. And the big difference between these, and this is how you can tell how do I solve it. Slope-intercept form says solve your equation for y. And standard form says solve your equation for the constant. Remember, a constant is anything that is not attached to a variable, right? So this is saying, I want to go to slope-intercept form, take whatever equation you're given and solve it for y. If I want to go to standard form, take whichever of these two equations you're given and solve for the constant. Okay, so let's just take an example. Let's say that we have 3x minus 4 is equal to y. Sorry, I put the y on the other side. In standard form. So we can never, it's never going to say put it in slope-intercept form. You can't, sorry, in point-slope form. You cannot do that. Notice point-slope form is not solved for an y. It's not solved for a constant. So we're going to put this in standard form. So here's what that means. The x's and y's are on one side. The constant is on the other. So we need to get the y over to the right, and we need to get the 4 over to the left. Okay? So here's how we do it. I'm going to do this in 2 separate steps. Okay? You can do it in 1 step, though. So the first thing that we're going to do is we are going to subtract y from both sides. That's going to get the y over to the correct side. Okay, so now what that gives us is 3x minus y minus 4 is equal to 0, right? Because y minus y is 0. Now we need to get the 4 over to the other side. So we're going to add 4 to both sides. That's going to get it out of the left and into the right. So now we have 3x minus y is equal to 4. And that's in standard form. This is our answer. Okay, we have the x first, right? 3x. We have the y second, minus y. Notice there's a plus sign, but our b is just -1 here, okay? Where our b is negative, which is why it turns into a minus. That's fine. And remember, this b is not a y-intercept, right? Our y-intercept is 4, But here we see a -1. Sorry, a -4. 3x minus y equals 4. This is solved for the constant. The constant is by itself. So we have 3x minus y is equal to 4. This is standard form. Okay. Let's do a different one. Y minus 4 is equal to 3 times x plus 2. Again, let's put it in standard form. So I want you to think about what form this is in now. This was in y-intercept form. Okay, it was solved for y. This one, it's not solved for y, it's not solved for constant. It is in point slope form. Okay, so we have to do a little bit of extra work here. First step is we have to get rid of parentheses. So we're going to distribute the 3. So we get y minus 4 is equal to 3x plus 6. So we got rid of parentheses first. This is to go from point slope to standard. In the first example, we went from slope-intercept to standard, so the only thing that we had to do was solve for the constant. Now we have to get rid of the parentheses first and then solve for the constant. Okay, and when we solve for the constant, what we're saying is get the constants on one side and the variables on the other. Okay, so we need to get the x over to the right, and we need to get rid of this 4, get it over, sorry, the x over to the left, and we need to get this 4 over to the right. So we can do that in one step if we want. We can subtract 3x from both sides. And we can add the 4, because then notice what's going to happen. The 4 is going to go away. 3x goes away here, and we add 4 to both sides. Okay. Now the next part is important. The x has to get written first. So when you're writing the x first, it would be written as -3x plus y. Okay. So instead of writing y minus 3x, you're writing it as -3x plus y. Just keep the sign that it has. The 3x has a negative sign in front of it. It stays that way. Okay, is equal to 10. And that's it. This is standard form. Okay. Some people will write it so that the x is always positive. So there are some people who will write 3x minus y equals -10. In other words, they multiply everything by -1. You can do that. That's 100% correct. I don't require it. I don't care. Okay. Let's take another example. Let's say that we have put y minus 2 is equal to 4 times x plus 1. And this time let's put it in slope-intercept form. So this is a little bit different. Okay, we're always getting rid of the parentheses, but this time instead of getting the variables on one side and the constants on the other, what we're going to do is we're going to solve for y. Okay, because that's the difference, and that's why I put this up here, that this is solved for y and this is solved for the constant, because it changes what we do, right? And it tells us very quickly how to get from one form to another. So here, we're going to get rid of the parentheses by distributing. You always get rid of parentheses by distributing when you're doing these simplifications. and then we're just solving for y. Okay, so when we get rid of the parentheses, we get y minus 2 is equal to 4x plus 4. And then we need to solve for y, which means get y by itself. So we just need to add 2 to both sides. So you can see none of this is all that complicated, right? These are just two-step problems. So when we add 2 to both sides, we get y is equal to 4x plus 6. Okay, so again, you're either getting your constants on one side and the variables on the other, or you're solving for y. Let's take a couple more. Let's say put 3x minus 4y equals 10 in slope-intercept form. Okay, and again, you're solving for y. Slope-intercept form says solve for y. So the first thing that we need to do, because we have to get y by itself, is subtract 3x from both sides. Okay, and remember, in slope-intercept form, we like the axis to come first, right? It's mx plus b, not b plus mx. So we get negative 4y is equal to negative 3x plus 10. And then we need to divide everything by negative 4. So do this individually. In other words, take the negative 3x, divide by negative 4, and take the 10 and divide by negative 4, because they're going to reduce differently, okay? And you want it to be written in the form of mx plus b, not in terms of, you know, not as a single fraction, okay? So what this is going to give us is y equals, and then negative 3 over negative 4, the negatives just go away. So we have 3/4 x. And then 10 over negative 4 simplifies. This is now negative, so it turns into a minus. And both 10 and 4 are divisible by 2. So minus 5/2. Okay, so you're solving for y, and sometimes you're going to get fractions. But notice that 3 over 4 simplified just by dropping the negatives. 10 over negative 4, you could actually divide everything by 2, which is why we do it separately. Okay. And finally, let's put this in standard form. So keep in mind what you're doing. Now, the easiest way to do this so that you are not dealing with fractions, because this is the first one that we've had where we're dealing with fractions, is get rid of your fractions, okay? Now, you know how to do that. You find the lowest common multiple, and here there's only one fraction, so it's easy, okay? Your denominator is 3. Your lowest common multiple of the denominators is 3. So get rid of denominators. You're not going to have any parentheses, right? Because this is an endpoint slope form. So if you have denominators, always get rid of those first so that you don't have to worry about adding and subtracting fractions. Okay, so get rid of your denominators. Then get the variables on one side and the constant on the other. And remember, you're going to have to get rid of the fractions anyway, because in your final points, in your final standard form, you cannot have any fractions. You can only have integers. So you're going to have to do this, whether you do it before you get the variables on one side and the constant on the other, or you do it after. That's up to you, okay? I kind of feel like it's easier, particularly if there's more than one fraction, to get rid of the denominators first, but it's up to you when you do it, but it has to be done, okay? Because we can't have a 2/3 x in standard form. That's not allowed. So we can multiply everything by 3. Okay, that's going to get rid of the denominator because we're going to get 6x over 3, which is just 2. So we get 3y is equal to 2x plus 21. And the most common mistake is people forget to distribute the 3 because they're so concerned about getting rid of the fraction that they forget to distribute the 3 to everything, okay? So we get 3y equals 2x plus 21, and then we just need to get the 2x over to the other side. So we're going to subtract 2x from both sides. So we get negative 2x, remember the x has to come first, plus 3y is equal to 21. Okay, now the next piece I'm actually not going to put in this video because I know that this one is already a little long. I'll put it in the next one, which will be a shorter video. But before I just close off, I just want to introduce you to the idea of parallel and perpendicular lines. Okay, so a parallel line when two lines are parallel, they actually have the same slope. So this is the only thing that I want to stick in here as the last piece. Parallel lines have the same slope. Okay, that's because they can never intersect, so they have to go up at the same rate. If they don't go up at the same rate and one is going up faster than the other, then it kind of makes sense that they're going to intersect at some point or another. Okay, now perpendicular lines have slopes that are negative reciprocals. So I'll explain that in a second. Okay, so parallel lines, by the way, we can denote or represent by two parallel lines like that. Parallel lines never touch. So it looks like this. When you see this, we're saying parallel lines. And perpendicular lines intersect at a 90-degree angle. So we use that, okay? So if the slope of a line is 3/4, then the slope of a parallel line would also be 3/4. If the slope is, I'll put in the word line here. If the slope of a line is -2/3, then the slope of the parallel line is -2/3. Okay, that should be pretty clear that it's just exactly the same. Okay, if the slope of a line is 3/4, then the slope of the perpendicular line is the negative reciprocal. So that what that means is that you flip your fraction, you're taking the reciprocal of the fraction, and you're making it negative. So 3/4 now has a negative sign in front of it, and we flip it. So it becomes -4/3. -2/3 Well, here it's the negative reciprocal. So if there already is a negative sign, then you take the negative sign away. So it's positive, and you flip it. So it becomes 3/2. If the slope of the line is 4, then it becomes negative because it was originally positive, and it becomes 1/4. If you have negative 1/2, then the slope of the perpendicular becomes positive. So you're flipping the sign and you're flipping the fraction. So it becomes positive 2. And before we go, here's why this happens. So when we say that we're taking the slope of the perpendicular line, I want you to look at this line, right? Right now, this line has a positive slope, and it's rise over run, right? It's the vertical distance over the horizontal distance, which gives us rise over run. What we're going to do is we're going to rotate this 90 degrees because that's the perpendicular. So I want you to look at what happens to the line. When we rotate it 90 degrees, the slope is no longer positive. The slope is now negative. That's the part where we say negative reciprocal. And notice what happened to the rise and the run. They switched. The run is now the rise, and the rise is now the run. So we have run over rise. That's where the fraction flips. Okay. So the fact that the slope went from positive to negative, that's the negative part. And then the fact that the rise and the run switch, that's the reciprocal part, right? If I rotate this 90 degrees again, well, this is a negative slope. If I rotate it 90 degrees, now it's a positive slope. Remember, we could tell whether it's positive or negative because when we go to the right, we're going up. That's a positive slope. Here, when we went to the right, if we were to go to the right, we would go down to meet the line, okay? So we rotate this 90 degrees. It went from a negative slope to a positive slope, and the rise and the run switched again. If we rotate it 90 degrees, this is positive. It's going to become negative. And once again, the rise and the run switch. Okay, so that's why we said that it's the negative reciprocal, because when we take a line and we rotate it 90 degrees perpendicular, then the slope goes from negative to positive, and it's a reciprocal because the rise and the run switch. Okay, and in the next video, what we'll do is we'll talk about if you're told that if you're given the equation of a line and you're told, hey, I want the equation of a perpendicular line, we'll look at how to find that, but that'll take a little bit too long here, and I'd rather put it in the next video. Okay, so simply stay tuned.